Well, we hear a lot about the Antarctic Peninsula. It is the area of the Southern Hemisphere has probably warmed more than anywhere else over the last 50 or 60 years. However, that's changed, and there's been a big change since the late 90s, and I want to talk a little bit about that. Even the newspapers are filled. You see on the web lots of reports about the Antarctic Peninsula and the warming. So these are just some I grabbed randomly. Global warming impacts in the Arctic and the Antarctic. This one intrigued me. This is Antarctic Peninsula, most Antarctic Peninsula warming human caused. And not all heating, warming on the Earth is caused by us. And so I wondered where this came from. This is in Nature, and it actually comes by Rob Mulvaney, one of my colleagues. And the actual abstract says this. He's looked at a 600-year record of temperatures. The high rate of warming over the past century is unusual, but not unprecedented in the context of natural climate variability the past 2 millennia. And so it says nothing at all about global warming. And so this is the problem we have. So we also see contrasting pieces like this. This is about, Rob collected his core on James Ross Island here at the tip of the peninsula. And ice core record, Antarctic Peninsula warming is nothing unusual. Press release flatly contradicts what boffins say. So we see all sorts of mixed messages about this. So I want to give you a bit of background to what's happened. For the last 50, 60 years, we all know where the Antarctic Peninsula is. It's south of South America. We were talking about South Georgia this morning. Signy Island is here where Orcadus is. The peninsula is about 2,000 kilometers in length. It rises to 2 kilometers high for much of its length. So it's a real substantial barrier to the climatological west to northwesterly flow. So the climates on the western side are quite different to those on the east. It's much more maritime on the western side. That's why we have the stations there. It's Rothera, Fossil Bluff, Faraday's up there I'll be talking about. And this is the length of in situ meteorological observations we've got for the Antarctic with the start dates shown in red here. And a lot of the stations were established around the time of the International Geophysical Year, big experiment, 1957 to 58, which was one of the great outcomes of the Cold War, the international cooperation, the establishment of stations by Russia, US, and lots of other nations. And we're lucky in the peninsula, we have some great records. There is Faraday Station, which is now Venadsky. We handed it over to the Ukrainian program, and that goes back to the late 40s. But the data is a bit patchy before that. So we really started using the data in 1951. We have Esperanza Station here, 53, Marambio, Argentinian, 71, and Bellingshausen Station, which is 69, the Russian station. So we've got a pretty good range of stations, but all on the coast. So it's not necessarily representative of interior areas. And the data, the monthly mean data for these stations is held in a SCAR database, which Dave and I set up decades ago, because there was lots of climate information on the web, temperatures, but you had no idea where they came from. You don't know the quality of the data, the quality control. So we went back to the various nations and got the 6-hourly meteorological observations, which are the most accurate. We quality controlled them, worked out the means, and put these on the web in this reader database. And this is just an example. This is the Faraday data, year on down the side. You probably won't see this. Months across the top. And for each temperature, we give the percentage of observations that were available for the month, which is quite important. The ones in red, you see, are less than, say, 80%. And we also provide metadata, because a lot of the stations moved, and that had made a subtle difference to the quality and the nature of the observations. To look at the broad scale meteorology over the ocean, we tend to use the reanalyses, the meteorological analyses. People have been producing weather charts since the 1950s, IGY, but there's hardly any data. Over the oceans, there was just the occasional ship, so you couldn't really draw weather charts like this with any confidence. But people gradually produced better analyses over the years. And now we have a series of high-quality atmospheric fields going back to 1979. They don't go back before that with any quality because there are so few observations over the ocean. People are trying to take them back, but this is a very safe period. And we're using the data from the European Centre for Medium-Range Weather Forecasting. So what I'll talk about is really what controls the variability of temperatures at these stations. There's lots of different factors come together. It's quite tricky. And then to look at the changes over this instrumental period and the mechanisms that we think are responsible. And then the cooling. It has cooled at a statistically significant rate. Certainly the stations in the northern part of the peninsula since the late 1990s. This is work we're just doing at the moment. And then to talk about how the models represent such changes or not. It's a very difficult, very challenging area, and what might happen in the future. So this is the mean atmospheric circulation for high southern latitudes. It's very similar throughout the year. There's a belt of storms called the circumpolar trough between about 60 and 70 degrees south. Pressures are slightly higher in the coastal area, and they rise as you go towards mid-latitudes. And so this is the circumpolar trough, and it's a mixture of storms that have developed in mid-latitude and move south, and also storms that develop here. It's a very stormy area. Anyone who sails to the Antarctic knows the storms you get, because it's a mixture here of warm air coming south and very cold air coming off the interior. So it's a very thermal gradient, very strong gradient, where you get a lot of storms spinning up. And there's a quite strong wave number 3 pattern. But the most significant area of storms is the Amundsen Sea Low. It's a bit like the Icelandic low of the North Atlantic, or the Aleutian low you get in the North Pacific. And so the winds go round in a clockwise fashion. And that's why we have our stations here on this western side, because it's covered by a relatively mild northerly flow, and we can get our ships in there. And so, of course, in the southern hemisphere, winds go around storms in a clockwise fashion. That's why we have the westerlies, low pressure here, higher pressure to the north. And the major factor that affects the climate of these stations is the Southern Annular Mode. This is I talk to a lot of biologists. They know about the SAM now. It's amazing. It warms my heart that there's such cross-disciplinary links now we're getting in this. This is basically, it's a natural mode of variability of the climate system, and it involves an oscillation of mass between the Antarctic and mid-latitudes, backwards and forwards. And it's called various things. It's been known as the Antarctic Oscillation or the high latitude mode, and it is the major factor that controls the climate of stations like South Georgia we were talking about this morning. And it goes between various phases of a positive SAM or a negative SAM. In a positive SAM phase, pressures, atmospheric pressures, such as we measure with a barometer, are relatively low over the Antarctic and high in mid-latitudes. So that it's an enhancement of the normal circulation, and the winds are stronger around the Antarctic. In the negative phase, pressures are higher over the Antarctic, and the westerlies are considerably weaker. But even though it's called an annular mode, and it's often worked out as the pressure difference between 40 degrees south and 65 south. And since we have a good range of pressures, the pressures are one of the primary quantities that we measure at the stations. The data we have from the coastal stations goes back to the 50s, and we have a series of island stations over the Southern Ocean that lets us work out this gradient of pressure. So we have a good SAM index back to 1957. But as I said, it's called an annular mode, but there's a non-annular element. So when the SAM is positive, we have a deeper Amundsen Sea Low, and we have warmer conditions on the Antarctic Peninsula. Warm air is drawn down. And the reverse is true when the SAM goes negative, in that we have a weak Amundsen Sea Low, we have more blocking, more anticyclonic conditions, so we have more southerly or weaker northerly winds. And that has a huge impact on the sea ice, because the sea ice has a major impact on the climate of the Antarctic, certainly on the coastal stations. And it's strongly moved by the winds. Sea ice in the Antarctic is not like the ice you get in the Arctic, which is quite thick. It's only 1 to 2 meters thick in the Antarctic. Most of it disappears by the end of the summer, and so it's often, a lot of it is 1 meter thick, so it's blown by the winds. And so when we have a SAM positive and winds like this, the ice is kept back towards the southern part of the Bellingshausen Sea. So the winds move it back, and the warmer air melts it slightly. And so these are the anomalies of sea ice for the year as a whole. When the SAM is negative, we have more sea ice. And so this has a huge impact on the temperatures at the coastal stations. But we also get impacts from the tropics. I was talking to Aaron about this. It's a very complicated signal. One of the largest climate cycles on Earth is the El Niño Southern Oscillation, which is a coupled atmosphere ocean cycle of the tropics. And we go through the El Nino phase and the La Nina phase. And it oscillates on a period of years on these sort of time scales. And during El Nino events, we have high temperatures near the dateline in the tropics here. And the reverse is when you have La Nina, when the warm temperatures move across towards Malaysia, and it's cooler in the Central Pacific. And this is the difference in 500 hectopascal height, or it's very similar to the changes in surface pressure between El Nino events in these years and La Nina events in these years. And the difference is seen as a series of waves. But this is just on average because each El Nino event is quite different. And so it's very difficult to generalize about these things. But if you look at these 5 most intense El Nino events and the El Nino and the La Nina events here, you get this sort of difference here. So during El Nino events, we have more high pressure to the west of the peninsula. And when we have La Nina, and Dave's published on all of this, that you get more storm activity. And of course, you get differences interacting between changes in the SAM and changes in El Nino. And so I've tried to summarize this here. You have a deeper Amundsen Sea Low, more storms here when the SAM is positive, or La Nina, and or La Nina. And you get a weaker Amundsen Sea Low when the SAM is negative, and you're in the El Nino phase. So we go backwards and forwards between El Nino events and La Nina. The SAM changes for natural reasons, but also for the ozone hole. One of the biggest impacts of the ozone hole has been that the SAM has gone positive. And so the Amundsen Sea Low has deepened with a contribution coming from the ozone hole. We did some experiments a few years ago where we ran an atmosphere-only model, and we kept, for the whole world, and we kept everything constant except ozone. And we ran with pre-industrial ozone, and then we ran with the ozone hole, and this is the difference you get at the surface. And you see the classic signal of the SAM. You get lower pressure when you have an ozone hole, lower pressure here. You get higher pressure in the mid-latitude areas, the subtropics. Strengthening of the winds. The winds over the Southern Ocean have increased by about 15 to 20% over the last 30 years, primarily because of the ozone hole. And you also get a deeper Amundsen Sea Low. People disagreed with this at the time, but people are sort of rather coming back to this now. And I think, when you get something like the Amundsen Sea Low deepened, there's no one single factor. There's multiple factors. You get changes from the tropics, you get changes from the ozone, and you also get natural variability. So it's always a balance between different factors, which means that this area here to the west of the Antarctic Peninsula, between the peninsula and the Ross Sea, we have the largest atmospheric variability of anywhere in the Southern Hemisphere. If you just look at the interannual variability of, say, mean sea level pressure, you get this area here, called the polar variability. And this is why our field seasons are so different in the Antarctic, in that we have some seasons where we go down in, say, October, November time. We can have fantastic weather, and we get lots of flying done, take people in the field. Other years it's just storm after storm. And so this is an area of intense atmospheric variability, which makes it difficult to separate human signals. Because a lot of people say, are we seeing a signal of anthropogenic activity, human activity? Is this greenhouse gas increases? We have a very large natural or intrinsic variability in this area. But Faraday, on the western side of the peninsula, is the classic station. We've got a very reliable, very complete, well understood record of surface temperature going back to 1951. And the green here shows the annual mean temperature, with the red showing a 5-year running mean. And it's warmed. It's warmed for the year as a whole by about 0.5 degree per decade. So it's a remarkable change. What we've lost are the very cold years that we used to have, -8, -7. We get occasional ones, but they've disappeared now. But it was even very variable, even in the early years. You could go from -2 down to -8 within a couple of years. And so you see all sorts of variability. I mean, this is, of course, in terms of climate, 50, 60 years is just a blink in the eye. But this just shows the variability on those sort of decadal timescales. And you can split those years into warm and cold years, upper quartile, lower quartile. During the warm years, you get this sort of, you get a SAM-like pattern here. That's shown because SAM is the major factor varying the climate system. And so when we have warm years at Faraday, we have a lot of storms to the west, high pressure here, warmer air coming down. So there's no great surprise there. In cold years, we have a distinct lack of storms here. So this Amundsen Sea Low area is a key area affecting the temperatures at Faraday. And you can look quickly at other stations. This is Bellingshausen, which is at the tip of the peninsula here. Very similar sort of pattern. All the stations have a very similar sort of signal. This is Esperanza, getting towards the tip. As you get towards the tip of the peninsula, you find that you get the winds crossing the peninsula being the key factor. You get this couplet of low pressure here to the north, warm, higher pressure to the south. So the winds getting over and down onto the area of the Larsen ice shelf becomes much more of a factor. And this is Marambio. Marambio is the most isolated of the stations. Faraday on the western side is very maritime. Esperanza is near the tip. Marambio is really round the corner, and it's much more affected by cold air coming up from the south. So there, really warm air getting over the top is the critical factor, but we still have this similar sort of patterns, the SAM, signal of the SAM, and storm activity to the west of the peninsula. And the links with the tropics, there are statistically significant links between the temperatures at the peninsula stations and what's going on in the tropics. This is the correlation of the Faraday annual mean temperature and sea surface temperatures everywhere around the world. And the bold line shows statistically significant correlations at the 5% level. And so what this is telling us is that there's an anti-correlation between Faraday temperatures and temperatures in this key area of El Nino. Anti-correlations with the temperatures at the dateline, correlations with temperatures over Malaysia, Indonesia. So I've tried to summarize this down here, the way this works, because during the La Nina phase, you have cold temperatures near the dateline. That sets up a wave trend which gives you deeper Amundsen Sea Low, little sea ice, and therefore higher temperatures at Faraday. So it's an anti-correlation between temperatures here and Faraday. And the reverse situation, you get higher temperatures during El Nino events here, more blocking here, more extensive sea ice, and lower temperatures. So this one factor, it's a statistically significant link. There's also links to Atlantic. There was a paper by Lee in Nature recently pointing out that this has a positive correlation. And when we do experiments, we can force in anomalies different places around the world. They all have an impact, but I think for me the signal of El Nino must be the largest. It's one of the largest climate cycles on Earth, and it has a significant impact. It doesn't explain everything, of course. And this is the correlation between Marambio temperatures, annual mean temperatures, and sea surface temperatures everywhere. And so we have a similar sort of pattern, but not quite so significant, because Marambio is getting removed from this tropical wave train. So the way it works is that during El Nino events, you have high sea surface temperatures near the dateline, you get a lot of convection, you get upper level divergence, and that establishes a wave train, a Rossby wave train, a chain of long meteorological waves from the tropics out into both hemispheres. And so we know that the climate of the USA is affected by El Nino events. It's the same in the Antarctic. So it's a very closely coupled system. You have signals coming in from the tropical Pacific Ocean, you have signals from El Nino affecting the area, and you also have natural intrinsic variability. Of course, this also is, El Nino is a natural signal. So any experiments, I would have to take that into account. But Faraday has a very clear annual cycle of temperatures. It's warmed a fair bit in summer, January, November, December time, about 0.2 per decade. But really we have incredible warming in the winter, July, middle of winter, almost 1.2 degrees per decade over 50 years, which is an astonishing amount of warming. And so we obviously have endless film crews who come down and say, look, global warming here. And we actually had a film crew on a boat, one of our small inflatables, going around the bay. And they were doing a piece on the boat, and some ice fell off a glacier. And the presenter turned around and said, look, global warming. And we said, no, it's a piece of ice that's broken off this little glacier. So not all the changes are caused by us. But it is an area of remarkable change. And there's a very, very strong link with sea ice. Sea ice is, the dominant factor here. If you correlate Faraday midwinter July temperatures with sea ice, not surprising, you get this huge anti-correlation. If you have a lot of sea ice, it caps the ocean, because the ocean underneath the sea ice is never colder than about minus 1.9. And the air above in the middle of winter can be minus 20, minus 30. So if you put sea ice there, it caps it, it's very cold. If you take the sea ice away, you get huge fluxes of heat out of the ocean. You get tremendous amount of heat input into the atmosphere. And so there's a huge significant anti-correlation between temperatures. So you also have a signal of the SAM here. You see often in ice cores, people who look at ice cores across the continent, they find this flip-flop between conditions in the peninsula and around the coast of East Antarctica. That is a classic signal of the Southern Annular Mode. And Susan Solomon looked at this in some of her papers as to what is the impact of the ozone hole. It affects us the SAM. We've had a cooling around the coast of East Antarctica, a warming in the peninsula. So the peninsula is always out of phase with the rest of the continent. And we can see the importance of sea ice if we look at the Faraday midwinter temperatures. If we just take 2 years like this one here, this is 1987, very cold, minus 14, ice everywhere. Capped the ocean, incredibly cold conditions. In contrast, 1998, it was very warm. That was a La Nina year. Very warm, almost minus 2, because there was no ice, just off the area of Faraday. Because in its annual cycle, sea ice retreats right back to the coast, just about, of the Bellingshausen Sea, and then advances north. Ice also comes round from the Weddell Sea, because we have the greatest amount of multi-year sea ice in the Antarctic in the Weddell Sea. And as storms go through the Drake Passage, you get ice coming round the corner, and they meet at Faraday. So purely by chance, Faraday is this area of incredible change. Conditions do change when you get to the tip of the peninsula. This is Esperanza. There the greatest warming has been in summer. It's quite different. They've hardly had any changes. In fact, it's cooled a little bit in winter. That's because the peninsula, the western side of the peninsula, is the only place in the Antarctic where the ice, through its annual cycle, goes up and down the coast. It retreats right back to the coast and goes right up to the tip, often, during its annual cycle. So it's like a switch there. But the stations at the tip are completely different. Even though they're not that far away, they're very dependent on ice, often that comes round from the Weddell Sea. And you can see this is Esperanza May, when it's had a warming. These aren't fantastic pictures, but this cold year, there's ice everywhere around the tip of the peninsula. Years like this is 2004. Then you have this area of clearance. And so sea ice has an incredible impact on these coastal stations. And sea ice has changed. It's disappeared a lot in February. We know that sea ice across the Arctic Ocean has disappeared very markedly, particularly in late summer, September. And it seems likely to be gone within a few decades, perhaps the middle of the century. Sea ice in the Antarctic has actually increased over the last 35 years. So we get reports that proves global warming isn't happening and things like that, which it doesn't at all. But it has changed a lot in summer. This is the February trends. We hardly have any sea ice now. This is negative trends. Sea ice has disappeared in the Bellingshausen Sea very markedly at the end of summer. And that's because we have a lot of radiation coming in. We're quite a long way south here. Ice albedo feedback works very well. In other words, if you get a slight decrease of ice because of stronger northerlies, it will expose the ocean, which is very dark. It absorbs a lot of heat. It'll cause this runaway effect. We recently had a cruise a few years ago to look at sea ice in the Bellingshausen Sea, and there was nothing there. They took a ship in and they had to go around into the Weddell to try and find some sea ice because it's gone so rapidly. But the strange thing is that overall, the Bellingshausen Sea hasn't really changed much in terms of total sea ice in the middle of winter. It's disappeared in the summer, but not in winter, except for just off Faraday, where it's disappeared. And that's very, very strange. Because in the Antarctic winter, once temperatures drop very, very rapidly, sea ice is going to form. There's no sunlight coming in, the air temperatures are very cold. If you're south of the Antarctic circumpolar current, it's going to be cold. But we have this strange anomaly. We have this little area of clearance now just off the station by chance. And that's because the growth is so very sensitive, and the nature of the sea ice growth has changed, because in the past there used to be more ice in this area in summer, but now that's gone. So the ice is right back to the coast, and it advects very quickly towards the north, and the peninsula curves around towards the east. And so the winds have changed so that it actually misses this little area here off Faraday, sometimes, not always. So we have this very strange situation where Faraday is incredibly sensitive to sea ice and has warmed up so much just because of this very local change in winter. But the Amundsen Sea Low has deepened. The storm activity has increased in that area, and that's difficult to understand. Over the years, it's not a statistically significant deepening of the Amundsen Sea Low, but nevertheless it has deepened. And so we have more storms in this area for various reasons. We think the ozone hole may have contributed, but only probably in the autumn period, because the ozone hole is a phenomenon of the southern spring. That's when the ozone is destroyed. The signal, we know, propagates down to the surface during the summer, but then it recovers. So it'll have had a small increase in the autumn or the fall at that time. Tropical sea surface temperatures haven't changed a lot, but they have gone slightly towards the La Nina phase, which will give slightly more storm activity in this area. But we also have a large natural variability, and it has deepened very rapidly in May and September. So we have this marked deepening here, and particularly September. September is the peak of the sea ice growth season, the minimum in February, but then it grows gradually, and this is a key time. The sea ice is out here, and it gets this real kick from the southerly flow in the Ross Sea, and this has played a major part in why sea ice has increased. Because we see lots, it's very confusing for the general public to try and understand this, because we've got Arctic sea ice disappearing, we've got Antarctic sea ice increasing at a statistically significant rate over the last 35 years. And this is the trend of sea ice from 79 to 2013. In the last 3 years, we've had record sea ice extents at a time when we've had record levels of greenhouse gases. So what journalists make of this is very difficult. But this is, the bold line shows the statistically significant areas of change. And 63% of the overall net increases in this area of the Ross Sea. Because we've had a change in the Amundsen Sea Low, that's the importance of the Amundsen Sea Low. It's decreased ice here, increased it in the Ross. And so certainly the trends in the Amundsen Sea Low in September must be important in this. So this is a complicated figure. So we were trying to work out whether the deepening of the Amundsen Sea Low is within the bounds of natural variability. And so we have very few records from my sort of work. We look at ice cores and get some data on sea ice, but it's very, very difficult. And it's very difficult to get a metric for the Amundsen Sea Low depth. So we've been looking at the models that are the basis of the Intergovernmental Panel on Climate Change. And we have 20,000 years of control runs. It's pre-industrial control runs of these models. Atmosphere, ocean, sea ice models. And these are all the different models on the side, from the Australian Access model down through Goddard models, UK Met Office, Japan, Russia. And they've been run in control mode for this number of years, many for 400 or 500 years, some for 1,000 years. And that gives you an idea of the natural variability. And this is the change in the depth of the Amundsen Sea Low over 35 years, because we only have 35 years of real data, and it's deepened by that red line there. It's deepened by half a hectopascal per decade. It's a rather modest change, but nevertheless it's had a huge impact. And so then we chopped the 20,000 years of control runs into 35-year pieces and looked at the deepening of the Amundsen Sea Low. And these little circles, they show the 2 standard deviation range of these trends. And what's happened in the real world is within the standard deviation, 2 standard deviation limit of every one of these models, which tells us that really it's not remarkable what the changes we've seen over the last 35 years. But then why should it be? 35 years is such a short time. And we also looked at the southerly winds over the Ross Sea, and they also were not remarkable. And people like Lorenzo Polvani have looked at the sea ice. Models have a great deal of difficulty in handling sea ice because slight errors in the ocean temperature or the air temperature or the winds or the ocean currents can give you huge errors in sea ice. But he looked at them anyway. He chose the best models, and he found that the increase we've seen over the last 35 years is nothing special. It's just, it sounds very dramatic that Antarctic sea ice is increasing at a time of record greenhouse gases, but we don't think it's anything remarkable at all. And so we have this impress with climate dynamics. This was rejected by GRL, so but what do they know? So I thought it was interesting. And so that's coming out soon. But the warming of the peninsula has slowed down. This is the trend in annual mean temperature for these 4 stations, Esperanza, Marambio, Bellingshausen, and Faraday, for the full length of the records. And you can see that they warm, but they've fallen since the late 90s. Particularly the stations at the tip of the peninsula. This is Marambio here, and this is Esperanza, and the decrease, and I can show it in a bit more detail here, is statistically significant at Marambio at the 5% level and Esperanza. Faraday has cooled a little bit over the period. Rother actually still is warming ever so slightly. But this is linear trends, so we have seen a cooling since the late 90s. There's no immediate point of transition, but I think it's sort of 97, 98, 99. And we're just about to submit this, and we've been looking at why. So this is the annual cycle of the temperature trends since 1998, to look at which part of the year the big changes have occurred in. And it seems to be this period at the start of the winter, between about April, May, June. It's most pronounced at Marambio, Esperanza, less so at Bellingshausen, and there's a different regime between the stations at the tip of the peninsula, Esperanza, Marambio, and somewhere like Rother or Faraday. They're controlled by sea ice moving north and south up the coast. So we've looked at this period in some detail. Sea ice is the key factor here. That this is the trend in April to June sea ice since 1998. And we've had this very marked increase of amount of ice in the Weddell Sea. And when you see this sort of couplet of increased ice to the south, decreased ice to the north, you know it's been moved south, and that's what's happened. It's actually quite difficult for us with our Halley station. Halley is here on the eastern side of the Weddell Sea, and we've had trouble getting in there. We just last season we had a ship going in at the end of the season trying to make a second call. We couldn't get in because of all the sea ice, and this early part of the growth season there's been more sea ice. Not surprising, it's caused by the winds. Winds drive the sea ice. These are the trends in the atmospheric circulation, the pressure. So we've had this low, high, low couplet, more storms here in the Drake Passage, and a very strong increase in the northerly winds, ramming the ice into the Weddell Sea, stopping it coming out. And these are significant. This bold line here is at the 5% level. So there's been a real change in atmospheric circulation, because normally we have a gyre here, the Weddell Gyre. The winds and the ice movement comes around the coast, down past Halley, up the coast of the eastern side of the peninsula, and then the ice gets swept away in the westerlies. And more ice is being kept into the Weddell Sea. And I showed the growth of ice before, and that you do still get storms going through, and that causes ice to come round into the bays around Esperanza and Marambio. And so really quite a modest change in ice has had a huge impact on temperatures. And so this, we still don't really understand all the reasons. We're running some diagnostics, looking at the waves generated here. It is a wave train all the way around here, going back to Australia over this particular period. These are significant anomalies, the bold line here, and going off here. So what's causing this is tricky. It's unclear whether this is just all tropical. Tropics will have played a part here, and so we're at the moment running some wave diagnostics information to try and see where this anomaly is established from. Because these anomalies, they're very controlled by the jets. Around a lot of the world you have just one jet. You've got the sort of polar front jet here, and that's the case in the Indian Ocean. But in the Pacific Ocean, the jet splits into two: a northerly subtropical jet and a southern polar front jet. And we know from work that people like Dave have done that El Nino events, you get a sort of flip-flop of these jets. During the La Nina phase, you get a stronger polar front jet, more storms down here. During the El Nino phase, you get a stronger subtropical jet. That affects the Hadley circulation around there. And so the jets have changed. We've had a strengthening of the polar front jet and a weakening of the subtropical jet, because we know that the right exit area of a jet is an area where we get storms developing. And so this marked strengthening of the polar front jet gives us more storm activity in the Amundsen Sea Low area, and has this marked effect. So why has this happened? Well, we have gone slightly towards La Nina, but I don't think that explains it all. It's quite interesting to understand what the natural variability of these jets is if you have fixed, perhaps Erin can tell us, so this we experiments where you get rid of El Nino. We're doing some experiments at the moment where we just run an aquaplanet, where we just have water everywhere and spin up the signal and then put in Antarctica. And then we can do experiments where we don't have El Nino, take away El Nino. Then you can get some handle on what is the natural variability of the jets to try and... The cause and effect is always the biggest problem here. There's never any one single answer to this, but this is what's happened in the real world. And so these are the trends in sea surface temperatures. This particular period, actually we've got slight warming here towards to El Nino. So I don't think that tropical conditions in themselves are really driving this. David Schneider's done some work suggesting that this signal here in the South Pacific is playing a part. But why has that happened? So it looks very much just like natural variability of the system, which is what we often come back to. But if all this is just natural variability, we have clues from the paleo records. This is some work from Liz Thomas, who's collected various ice cores. Farino is here, this record here. Gomez, some cores we've collected. Trying to get a signal of the Amundsen Sea Low. And Farino, Liz published this, and I was involved with this. And she wanted to be able to say that it's unprecedented what's happened and get her paper in Nature, but it wasn't. She was rather disappointed that 300 years ago there was a 50-year period of warming which was greater than what we've seen over the last 50 years. So she got that in GRL, which is quite nice. So, but she was still fairly happy. But that's the nature of the system. So there is a very large natural intrinsic variability in this area. So how do the models, we do a lot of this modeling work to help IPCC and work out what's going to happen in the future. Obviously they struggle with the peninsula because they have a relatively coarse horizontal resolution. A lot of the models have a peninsula that's only say 1 kilometer high, and they don't have good Amundsen Sea Low, and they don't have a good El Nino. The previous IPCC report, 2007 I think it was a lot of the models didn't have El Nino. Now they seem to be getting variability in the tropics on the scale of El Nino, which is good. Some of them have real problems still, but they're getting that in now, which is good. But this is what the models have in terms of mean sea level pressure changes from 79 to 2004 in just 6 of the models I found at random. So models like, this is the real world. This is a European Centre Reanalyses. They have an Amundsen Sea Low. HADGEM2 is not actually bad. That's from the Hadley Centre in Bracknell. That has a good Amundsen Sea Low. CCSM4 model doesn't seem to have any Amundsen Sea Low deepening because the SAM has gone positive. So we should be seeing a SAM-like signal like this, which is quite good. But CCSM4 doesn't seem to have that. Access's Australian model has a good Amundsen Sea Low deepening. MPI is the Max Planck Institute. I don't know what's happening in that model. That's very strange, and this is one of the other models. So the models are very variable in what they've done. They all have the ozone hole in them now. So they should have the SAM going positive like that, but some of them don't. Perhaps for other reasons. There's never any simple answer when you have problems with these models. So the future, what will happen in the future? That's very, very difficult. We have a large natural intrinsic variability in the area. And so it could go really any way. We expect the ozone hole to heal by about 2050, 2060. So we expect that impact on the system to disappear. However, it seems very likely the greenhouse gas concentrations will increase. And the models suggest, if we trust the models, the SAM will go even more positive. So we could have a more deepening of the Amundsen Sea Low for that reason. We don't know what will happen to ENSO. If you ask questions like, will we have more El Nino events, the models just don't give a consistent view at the moment. And then we have natural variability. Since it's so tied with sea ice, we believe that maybe 1/3 of Antarctic sea ice will disappear by the end of the century. The models are quite variable on that, but that seems consistent. But of course, the models, when they run from 1979 to the present, don't have the increase of Antarctic sea ice. But if that's just natural variability, then would we expect that? Because of all the models we have within IPCC, about 5% have Antarctic sea ice increasing, 95% have it decreasing, rather like the Arctic, over the period since 1979. So it's still a little bit of anomalous. I think we're not really sure about this Antarctic sea ice increase. Why do we get more of the models getting an increase? So I think we need a lot more work on sea ice in models. But if we do get more sea ice disappearing, then somewhere like the rapid warming we've seen of Faraday won't come back, I don't think. Rather further south is warming slightly still, but I think that may stop, but we just don't know. So yes, we think we will get an increase of the winds around the Antarctic and probably a decrease of about 1/3 of the sea ice. So if you look at the models for the future, I'm drawn to a close here. If you look at, this is just a range of the models. This is the 1.5 meter air temperature. What they predict changes between the last 30 years of the 20th century and the last 30 years of this century. There's a lot of red, so they go for warming. There's some clear outliers, like these models here. This is GFDLs. I think that had some well-known error. Because the biologists we work with, they often say, well, what's going to happen on Cygnus Island? And we can say that these models, they suggest a warming of 3 to 4 degrees if we have a moderate increase of greenhouse gases. But these show really no consistent signal on a regional level. And if you're a biologist, you want to know really what's going to happen in the peninsula, say. And but then maybe this is variable. We often say it's a pity we only have one Earth running. If we had a number of Earths running in parallel, we'd get an idea of the variability. But we do have models. If we trust the models, and we just start the models off with just random data, and we run some of these models maybe 100 times, they go in different ways. That gives us a whole ensemble of predictions. And that's surprisingly large, which really probably shouldn't surprise us from what we know from the paleo records. So we think that the climate system, if these models have the same sort of internal variability as the Earth, are giving a real reflection of what's going to happen, and that it could be any of these which is the correct solution to what happens. So I think regional prediction may not be feasible. Perhaps we can say for the Antarctic as a whole, but if you want to know which sector of the continent is going to warm the most, that may not be the case. So conclusions, well, it is, they have experienced this remarkable warming over the full length of the records, but there is this cooling, statistically significant cooling, especially at the tip of the peninsula since the late 90s. And sea ice is the key. Faraday, rather, are very different from Bellingshausen, Esperanza, Marambio because of the sea ice regimes they're in. Sea ice key. And it is surprising, but maybe it's not surprising that very slight changes in atmospheric circulation can have a huge impact on temperatures because slight changes in sea ice. Sea ice is like a switch, especially in winter. And so these modest circulation changes have had this fantastic effect. I think it's generally understood that the ozone hole has had the greater impact than greenhouse gases. People like Arblaster and Meal have run coupled models with individual forcing factors. They've just run it with an ozone hole separately, greenhouse gases, solar, aerosols, and so on. And by far the largest impact has been the ozone hole. So that's going to heal by the middle of the century, and then greenhouse gases, the next most important factor, will really kick in. So it'll be a period of transition over the next 50 years or so. But a very large natural or intrinsic variability in the system. So I think it's going to be more difficult to see real anthropogenic signals in the polar regions than at lower latitudes because of the natural variability here. And regional scale may be very difficult to give reliable predictions that people want. So I'll leave it there. Thank you.